Well, hello everyone. Today's lecture is about mixing, and this is a situation that we often encounter in air conditioning systems. So this week in the lab you will be performing experiments on mixing, which is a very basic psychrometric procedure. So at first I want to tell you how a typical air handling system looks like, and we look at the most basic air handling system. It's called one which uses 100% outside air. So we'll start the lecture, which is about adiabatic mixing. And what I'm going to do is I'll draw you a very elementary air handling unit. So we'll start out with a space that we want to condition. So we call this a conditioned space. And this can be anywhere, anything from a single lab, it can be a classroom, it can be a whole suite of rooms, something which we would call a zone. And into this space, we are bringing air. And we bring this air from our air handling unit. And the ducts, in general, I will just show as lines, like this here. But the air handling unit, I'm just drawing out to give you a sense of how this looks like. So we have a fairly big ductwork for the air handling unit. And we have a fan. When we bring in air from the outside, we're bringing in air from the outside, then we first send it through a filter to remove particulates in the air. And then, depending on what we want to do, we may have a cooling coil. And as we discussed in class, let's say this is a summer air conditioning situation. We bring in air from the outside, which may be at a temperature, dry bulb temperature of 90 degrees Fahrenheit. We want to cool it down and remove humidity. So what we would have is we remove heat from it. But we are also removing water. And quite often the air gets cooled down to temperatures of around 45 degrees Fahrenheit and has fairly high humidity. So typically what we want to do is we want to reheat the air. Yeah? So we have a reheat coil. Okay, so you can use this kind of an air handling system for summer cooling situations, but also for winter heating situations. You would just not run chilled water through your cooling coil and instead run only hot water through the reheat coil, and that would likely do it in order to get you air for winter heating conditions. So in summer, typically we want the air to go into the fan and then be brought into the room at temperatures of around 55 degrees Fahrenheit. In winter, for commercial buildings, we may let this go up to 65 degrees Fahrenheit. It's still below 75 degrees that we typically have in a room, because in commercial buildings we have lots of heat generation through lights, through computers, through people. So we still bring in somewhat cooler air in order to remove that heat. So the conditioned air from our fan goes into the conditioned space. there it mixes with the already present air, and we assume that then the perfectly mixed air leaves again from the conditioned space and is discharged to the outside. So this is a situation that we call 100% outside air. And while you already see that we do a lot of work to condition the air, we bring in the air from the outside, we may cool it down, which requires energy, and then we reheat it, which requires energy, and then we bring that air into the space, and then we just take this conditioned air and we discharge it again to the outside. So that may seem like a waste of energy to you, and you are absolutely correct. But unfortunately, there are situations where you need to have 100% outside air because it's required by code. And this is, for instance, 100% outside air is a situation that you will use in laboratory buildings like the renovated mechanical engineering building where we have our lectures. There, everything north of the corridor is laboratory space. And in these spaces, you do not want to take air from one lab into another lab because if you have something like a chemical spill or something like this, then you don't want to take contaminated air and distribute it all through the building. So code requires that for situations like laboratories, hospital operating rooms, clean rooms, you have 100% outside air, okay? So required by code for laboratories, hospitals, and so on. So there's clearly quite a bit of energy loss going on, and sometimes, or nowadays almost always, you try to remediate that situation by recovering some of the energy from the conditioned air that you're discharging. So in the summer, you would like to recover some of the lack of energy that you have in the cold air compared to the warm air. And in the winter, you like to recover some of the heat and actually preheat the outside air. And you can do this by having a set of heat exchangers. So I'm drawing two heat exchangers here and something which is called a runaround loop. Okay. So we would need a pump here. And we just have our fluid, a working fluid, something like a glycol water solution, run around in this loop, and in the winter pick up some of the heat from the air which comes from the conditioned space and pick up that heat, and I'll draw this here as Q dot, and you're putting it into your glycol solution, and then you're using that heat to preheat the outside air. So you can use this runaround loop with two heat exchangers, or as we have seen or will be seeing when we take the tour of our air handling unit in the mechanical engineering building, we use something which is called a heat wheel. And the heat wheel is the same thing as the desiccant wheel, so it rotates between the incoming airstream and the outgoing airstream and exchanges the heat this way. And the efficiency of these devices is somewhere between 60 to 80% if it gets very good. So you're making up for quite a bit of the losses of energy. So this is a situation with 100% outside air. You can reduce energy losses by that in that situation if you don't discharge all of the air to the outside. And that is a situation that we call recirculating air. And in that case, we're taking some of the air that we usually would discharge to the outside and we recirculate it through the building. And this is something you can do when you are dealing with space which is not laboratory space, where you don't have chemicals released. So that means office space, classrooms. That's the situation which you actually have in your houses, where you have 100% recirculated air typically. In commercial building, you would not take the entire air and recirculate it. So let's take a look at how a system like this looks like. So this is a recirculating air handling system. Okay, and again we have our conditioned space. We're bringing in air and we're taking out air, and part of the air is discharged to the outside, but we're also splitting off some of the air and have some of the air join the air that we are bringing into the building. So again, here we're taking in air from the outside. Okay. And here we have our air handling unit again. So we have our filters. We have the cooling coil. The reheat coil. And our fan. And we're bringing the air with that fan into our conditioned space. Okay? So typically what you will do is you will recirculate somewhere between 60 to 80% of the air. So let's say this mass flow rate is 60 to 80% of the air, and that means you're discharging only roughly 20 to 40% of the conditioned air. And so immediately you see that, let's say you're discharging only 20% of the air and 80% is recirculated. Immediately you see that you're saving energy because you have put all this energy into conditioning the air, and instead of discharging it all, you're only discharging about a fifth. Okay? So the situation that we encounter when we bring the recirculated air and the outside air together is called mixing. So we have the recirculated air here and outside air here, and we're bringing them together at this point. And well, I think you get the idea. So we're bringing it together right here. And this is where mixing happens. And now we want to understand how the mixing process works, okay? So the mixing is something that we typically want to consider as adiabatic. So we assume that we take the air, two air streams, bringing them together, we're mixing them, but there is no exchange with the ductwork and so on. So it's all happening adiabatically, okay? So typically we think of this process as such that we have two ducts coming together, and we're bringing in air from the left, and everything is nice and insulated so that it's easy to consider this situation. So we have an airstream, and I draw a control volume here. Maybe I do that in red, so we'll draw a control volume here. We look at one big control volume. Okay. And we're bringing in two airstreams, and one airstream 1 comes with a temperature T1, and it comes with a certain amount of humidity. And I remind you, we had talked about the humidity ratio, W1. And again, what was W? W, the humidity ratio, is the mass of water divided by the mass of dry air. Okay, so that's a reminder. We talked about this some weeks ago, but well, people forget. Okay, so we have an airstream coming in with a temperature T1 and humidity ratio W1, and an airstream T2 with humidity ratio W2 entering our control volume here. And then we assume that the two airstreams perfectly mix, and they leave with a temperature T3 and a humidity ratio W3. So there are two ways to describe this process, and one is an algebraic solution. What we're going to do is we just look at the mass balance and we look at the energy balance equation, and that helps us understand this process. But the second way of solving or considering this problem is through the psychrometric chart. And so I want to show you how this process looks like on the psychrometric chart, and you probably will agree that it is actually a very easy way of looking at this problem. So let's start with the algebraic solution. So we start with mass balances, and we need to consider two mass balances. One is for dry air and the other one is for the water vapor, okay? So let's start out with mass balance. Now we're looking at dry air. And that mass balance is real simple. It's m dot A1 plus m dot A2 is equal m dot A3. Okay? And then we have the water vapor. And it's very similar. It's m dot W1 plus m dot W2 is equal m dot W3. Well, of course I can write this in terms of humidity ratios. Okay, so let me write it with the humidity ratio. So then this mass balance becomes m dot A times W1, and that's m dot A1 actually, plus m dot A2 W2 is equal m dot A3 W3, okay? Now what I can do is in the mass balance for the water vapor, I can replace m dot A3 with what I have from the mass balance for dry air. Okay, so let me do this real quick. And then what I get is overall for the mass balances, m dot A1 W1 plus m dot A2 W2 is equal m dot A1 plus m dot A2 times W3. Okay? So if you know, or if you measure the mass flow rates of the airstreams A1 and A2, and if you measure the humidity, the relative humidity or the humidity ratio, then you are able to take the mass balance and just solve it for W3. Okay? So, easy enough. Unfortunately, I didn't leave enough space for the energy balance. So, well, maybe I just squeeze it down here. No, it's not going to work, so I'll move it to the next page. Yeah. So energy balance is obviously equally simple. The energy balance so we have the energy coming in with the first airstream m dot A1 times H1 plus m dot A2 times H2 is m dot A3 times H3. Okay. So, and here I can do the same trick as I did a minute ago. I can replace m dot A3 on the right hand side, and I end up with an equation m dot A1 H1 plus m dot A2 H2 is equal m dot A1 plus m dot A2 times H3. Okay? So, and you may ask, well, what about the water vapor and so on? Remember that the way how the enthalpy is defined, the contribution of water vapor is included in that. Okay, so we don't need to worry about it. That's all included in the enthalpy. Okay? So again, we could, if we know the temperatures and humidities and the mass flow rates of the airstreams 1 and 2, we can calculate the enthalpy of the outgoing airstream, H3, and with that you could then, for instance, from the psychrometric chart and so on, you could in principle figure out what the temperature is, okay? Good, so this is the algebraic solution, so you're just going and you solve the mass and the energy balances, okay? But I want to look at how this actually may look like in the psychrometric chart, because we'll find that you can very easily describe this process in the psychrometric chart, okay? So what I want to do is, so we're pretty much done with the algebraic solution at that point, and now we look at the graphical solution in the psychrometric chart. But in order to understand how we represent this process in the psychrometric chart, I want to manipulate the mass and the energy balance, because that helps us understand how the process is graphically represented. So what I want to do is I want to take the mass and the energy balance, and I want to bring all terms with m dot A1 to the left-hand side and all the terms with m dot A2 to the right-hand side, okay? So because I have the energy balance up here right now, I'll start with that, but then I'll just copy what we had from the mass energy, okay? From the mass balance equation. So if I bring these terms to the left-hand side, everything which comes with m dot A1, then I have m dot A1 times H1, and I bring a minus H3 from the right-hand side, okay? And so equally, now I have on the right-hand side m dot A2, and here I have H3 minus H2, okay? Good. So if I go back to the mass balance equation, I see that it has exactly the equivalent form, right? So I'll look at this equation down here and I bring it to the other page and I manipulate it, but it's absolutely equivalent to the energy balance, just that my H's are replaced by W's, okay? So this is energy here, from the mass balance, I find m dot A1 is times W1 minus W3 is equal to m dot A2 times W3 minus W2. Okay, so very nice. So actually, this is really nice. What I can do here now is, if you look at these equations, it always says left-hand side is equal to right-hand side. So if I take these two equations and I divide them by each other, then, well, it's still an equation, right? So I can take these two and I just divide them. Okay? So what I get here, let's take a look here. I get W1 minus W3 over H1 minus H3 is equal W3 minus W2 over H3 minus H2. Okay? Very good. So what do we get from that? Let me see. I want to flip this around. Yeah, you don't mind if I just flip it around. I'll do it like this. H1 minus H3 over W1 minus W3 is equal to H3 minus H2 over W3 minus W2, okay? So it's still an equation. All what I did is I flipped it around, okay? So if you look at this, H1 minus, and I know it's hard to read, this was H3 over W3, and H3 minus H2 over W3 minus W2. So does that remind you of anything? That's the big question, right? What if I would, instead of calling this H and W, I would call it X and Y, yeah? So what would this remind you of? Okay, so you may say, maybe that reminds you of a slope of a straight line, right? Okay. Yeah, correct. This looks like the slope of a straight line if your variables would be H and W. And it turns out that in your psychrometric chart, these are actually, if you remember what we talked about a few weeks ago, these are the fundamental variables. The humidity ratio, W, and the enthalpy, okay? So, unfortunately, while these are the fundamental variables, they are not necessarily the variables which give you the perpendicular axes. So if you remember our psychrometric chart, we had the humidity ratio over here, and on the horizontal axis here we had the temperature, the dry bulb temperature, right? But even though it almost looks linear, if you very closely look at it, this is really not the linear variable. There's some slight variation from linear. The real second linear variable in the psychrometric chart is actually the enthalpy. Okay, and the enthalpy was up here, okay, with an axis here. And remember, we had the saturation line, phi equal 100% up here. We have lines of constant enthalpy and constant wet bulb temperature, and they look something like this, H equal constant. But the way how the psychrometric charts are constructed is that W and H, they are the linear variables. And that's specifically done for the purpose of psychrometric problems where the enthalpy and the moisture are really the critical pieces that you consider. So in this kind of diagram, even though the axes are not normal to each other, but they're tilted at an angle, the straight line is still the straight line, okay? So, and if we go back to what we learned here, this pretty much means that the right-hand side means that the line that you have between states 2 and 3 is the same as the line, or has the same slope as the line between states 1 and 3, okay? And so that actually implies that all these three states, they lie on one line in the psychrometric chart, okay? So if I have two air streams, and let's say we think back of our air conditioning situation where we bring cold outside air. Let's say we're in the winter now, we bring in cold outside air and we mix that with air which has been heated and is being recirculated. Then your cold outside air, let's say this would be your state 1, is somewhere here. And your conditioned air, which you consider, that's your state 2, that's over here, okay? So, and after the mixing process, we know that all three states which we have in this problem will lie on a straight line, and we call this line the mixing line. Okay, so this is the so-called mixing line. Okay, so your point 3 will be somewhere on this line, and I'll maybe put it over here. So this is your state 3. And again, if we go back to our diagram, if you look at this, we bring in air streams 1 and 2, okay, and they're mixing, and then we have mixed air with properties at state 3. So in state 3 has to be somewhere on the mixing line, the straight line between the states 1 and 2, okay? Where state 3 is, that really depends on a number of things. It depends on the mass flow rates of the two air streams. Yeah? So if you have a lot of recirculated air, and let's say you're recirculating 80% of your air and you're mixing that with 20% outside air, then your state 3 will be very close to state number 2. Okay? If, on the other hand, you're recirculating only very little air, let's say only 10% of the air is recirculated and mixes with 90% of the outside air, then your state 3 will be very close to state number 1. But it has to move somewhere on the mixing line, okay? So, and in this week's lab, you will actually measure the properties of the air which we bring in from the outside air, and the air which we are recirculating. And what you should be doing in the lab is you should be checking if all of these things actually work out the way how I described it to you. And if the laws of nature still hold, it should work out, okay? But you can also think about, well, is the process that we have, is it actually really adiabatic mixing? Or maybe do we have, while the mixing occurs, heat diffusing in through the ducts and so on. So all of these things can happen, and there can be small variations from what I described to you here. But the basic process is as described here. You have the mixing line, and your state 3 needs to be somewhere on the mixing line. Okay? So to summarize, you have two ways to treat the problem. You can do the algebraic solution. You take the mass balances, the energy balances, you solve them for the properties of the mixed air, or you have the graphical solution. In the psychrometric chart, you determine your states 1 and 2. The original state, state 3, needs to be somewhere on the mixing line. Okay, I hope that makes sense. I hope lab will go well, and thank you for your attention.